Hi, my name is Taylor Slaney, and I'm going to be presenting Week 15's project on spectroscopy, combined spectral problems using data from Group 7. On this slide, we see our molecular formula, which is C9H12, but we are unsure of the structure this chemical formula represents. This project has asked me to identify the structure that matches this chemical formula using the data that is provided. 3 data sets were given to help us solve this unknown compound: an IR spectra, 13C NMR, and 1H NMR spectra. So here again we see our molecular formula, which is 9 carbons and 12 hydrogens. In this slide I have calculated the degrees of unsaturation as well as the sites of unsaturation. Degrees of unsaturation is a method that can be used to help solve an unknown molecule. Degrees of unsaturation indicate the total number of pi bonds and the rings within a molecule, which can make it easier to then figure out the molecular structure of an unknown compound. To calculate the degrees of unsaturation, we will be looking at the number of carbons, nitrogens, halogens, and hydrogens. So in our molecular formula, we have 9 carbons, no nitrogens, no halogens, and 12 hydrogens. I've added the chemical formula here in the PowerPoint, and so with our chemical formula, we have 9 times 2 for the 9 carbons, plus 2, which gives us 20. We then subtract 12, which gives us 8, and then divide that by 2, which gives us 4. We also get 4 when we calculate the sites of unsaturation, which is 2 carbons plus 2 minus or subtract the hydrogens divided by 2. Using this formula with our molecular formula, we have 9 times 2 plus 2 subtracted by 12 divided by 2, which again equals 4. So, what does this mean? 4 degrees of unsaturation is a good indicator that our unknown structure has a benzene ring because of its 6 carbons and 4 degrees of unsaturation, with a 1 ring and 3 double bonds. However, even though we know that our structure most likely has a benzene ring, we still don't know what our molecule is. That is why we will be looking at IR, 13C NMR, and 1H spectroscopy to help us identify our molecule. So infrared spectroscopy, or IR spectroscopy, is the measurement of the interactions of infrared radiation with matter by absorption, emission, or reflection. The IR spectrum measures the vibrations of atoms, and based on this can help determine the functional groups in a molecule. So looking at the IR graph that was given to us, we again see a benzene ring with alternating single and double carbon bonds, and we start to see a CH alkene side chain. The peak to the left at 3,100 to 3,030 shows an aryl CH stretch vibration. The peak at 2,900 to 2,845 demonstrates the stretching vibration of an alkene CH to CH3 bond. Peak 1,600 to 1,500 is the aromatic benzene ring that we discovered in our degrees of unsaturation calculations earlier. And then peaks 1,400 to 1,370 and 110 to 690 show even more evidence of a benzene ring with an alkene side chain. 13C NMR spectroscopy is another powerful analytic technique that is used to study structures and connectivity of organic molecules. In 13C NMR spectroscopy, carbon atoms resonate a characteristic frequency based on their local chemical environments, which is influenced by neighboring atoms and functional groups. These resonances appear as peaks in the NMR spectrum, which then provides information about the types of carbon atoms present and their surroundings. By analyzing the chemical shifts, intensities, and coupling patterns of these peaks, chemists can figure out crucial structural details such as the number and types of carbon atoms, their connectivity, and the presence of certain functional groups. This information is essential for determining the molecular structure and understanding chemical properties and their reactivities. In the 13C NMR spectroscopy that we received for this data set, we see 7 peaks, which indicate 7 different environments for the carbons in our compound. The first 4 peaks represent the chemical shift from 142 ppm to 125.7 ppm, indicate alternating single and double carbon bonds for the benzene ring. Peaks at 38.2 ppm, 24.6 ppm, and 13.8 ppm give more evidence of an alkene propyl group. Finally, we have our fourth and last data set that can help wrap up this mystery of an unknown compound. The last data set is 1H-NMR spectroscopy, which is another technology that can help us determine the structure of a chemical compound. 1H-NMR looks more at the hydrogen environments in a compound and how those hydrogens interact and bind with other elements in the compound. In the table we see 4 peaks for the 4 different environments the hydrogens are in. When looking at the table from left to right, we have an integration of 5H, 2H, 2H, 3H. The peak at the far left, 7.02 to 7.5 ppm, indicates a benzene ring with 5 carbons. We can now infer that one of the hydrogen bonds from the benzene ring is missing because of an alkene propyl group coming from the benzene ring that has 2 hydrogens coming from the carbon closest to the ring at peak 2.57 ppm and 2 hydrogens coming from the middle carbon in the alkene propyl group at peak 1.64 ppm. This is split into a 1,5,10,10,5,1 sextet by the CH2 and CH3 protons on either side. Finally, the last peak at 0.94 ppm indicates our methyl group of 1 carbon and 3 hydrogens with a split of 1,2,1 triplet because of the adjacent CH2 protons. So let's put all the pieces together. What is our unknown compound? We know that our unknown compound has 9 carbons and 12 hydrogens. We know that 6 of those carbons and 5 of those hydrogens are used in the benzene ring, leaving us with 3 carbons and 7 hydrogens. We also found evidence of an alkene propyl group coming from the benzene ring. So, what do you guys think it is? Propylbenzene. So if you guess propylbenzene, you're right. Our unknown compound is propylbenzene. Propylbenzene is a clear and colorless liquid that is insoluble in water with a density of 0.8620 grams per cubic centimeters, a melting point of negative 99.5 degrees Celsius, and a boiling point of 159.2 degrees Celsius. So that concludes my presentation on spectroscopy combined spectral problems using the data from Group 7. I hope you enjoyed my presentation and saw the amazing techniques and technologies that we have available to us as scientists when discovering unknown compounds. Thank you and have a great day.